Hello everyone, I'm Yifan from Institute for Infocom Research, ISTA. Today, I'm going to introduce our work on source-free domain-adaptive semantic segmentation via cross-modal consistency training. To cope with data sharing restrictions, recent efforts have investigated source-free domain adaptation, which transfers knowledge from a well-trained source model rather than from the source data itself to an unlabeled target domain. In this work, we propose to utilize self-supervised depth estimation to improve the performance of semantic segmentation. As shown in the figure on the right, existing depth-aware semantic segmentation for typical UDA mainly adopts a multitask learning framework, where depth estimation is modeled as an auxiliary task. Comparatively, we introduce a multimodal auxiliary network that takes depth modality as an additional input for effective pseudo-label denoising and consistency regularization. Let X denote the target dataset, where Xi, Di represent the RGB and the depth modality of the S sample respectively. Our goal is to adapt a unimodal source model to a unimodal target model more robustly via a multimodal auxiliary network. To achieve this goal, we present a novel two-stream neural network with a main stream and an auxiliary stream that perform semantic segmentation based on RGB and RGBD modalities, respectively. Facilitated by the depth modality, pseudo-labels obtained from the source model can be better rectified, leading to improved source-free UDA performance. Moreover, the auxiliary stream is only required during training and will be discarded at inference time. Thus, our inference stage model shares the same network architecture but obtains improved segmentation results compared to the prior art. The figure below shows the architecture of our proposed framework. Our method consists of two major components: the cross-modal consistency regularization and the dual-head pseudo-label denoising. Given an unlabeled target image X, we perturb it based on strong and weak augmentations and feed them to the target network and its mean teacher model respectively. Let P-image and P-aux denote the output of the main and auxiliary streams respectively. P-tilde-image and P-tilde-aux are the output of the mean teacher model. The cross-modal consistency is formulated as the KL divergence between the P-tilde-aux and P-image plus the KL divergence between the P-tilde-image and P-aux. Though the pseudo-labels generated by the source model can be directly used to train the target network, rectifying it from a parallel aspect to consistency training will gain additional benefits. To this end, we adapt a recent state-of-the-art prototypical pseudo-label denoising method to our framework. This approach fixes the pseudo-label and rectifies it based on class-wise dynamic weights. The equation is given below. The weights for the two heads are computed based on the feature distance to the class prototypes, as shown below. Here it shows the experimental results. We use the GTA5 as the source dataset and the cityscapes as the target dataset. We compare our proposed method to both source-free and non-source-free domain-adaptive semantic segmentation models. As we can see that our method outperformed the existing method by a large margin. This table shows the results obtained by using the Cynthia dataset to train the source model. Finally, we visualize the monodepths, the stereo depths, and the visual depths of the cityscape dataset that we used in our experiment. We also visualize the corresponding HHA representations. In the figure below, we visualize the results obtained by the source model, the second-best model, our model, and the ground truth for a qualitative comparison. Thank you.